Now with everything that we've talked about, we can start to explain where elements come from. So chemists worry about how it is that the elements combine and react together in the different materials they make. But in astronomy, we get to explain where the elements come from. So all elements are actually produced through astronomical processes. From the first few minutes after the Big Bang, we have all of the hydrogen and helium produced. Now that's something that we're going to have to explain more. We'll get into better detail later on when we talk about the Big Bang. Now, we've mentioned previously that as all stars are on the main sequence, they convert hydrogen into helium, and then eventually, once the hydrogen is used up, they'll convert helium into carbon. Then we saw with high mass stars that we have the CNO cycle, where we're producing carbon, nitrogen, and oxygen. Then, in these high mass stars, we're able to continue fusion through helium capture. Helium capture is what it sounds like. The nucleus captures a helium. So carbon with a helium turns into oxygen. Oxygen with a helium turns into neon. Neon with a helium turns into magnesium, and so on, slowly building up the nucleus larger and larger and larger. Now this process will go all the way up until iron. Remember, in a high mass star, where the core is never going to be able to fuse iron. Iron is an energy sink. It does not actually produce energy. So once the core is iron, fusion in the core ends. Then, during a supernova, we have so much excess energy that we're able to fuse iron together. Remember, it does not release energy, but we have so much excess energy it doesn't matter, and then we're able to produce everything else on the periodic table. Okay, so, for example, people really like silver, gold, and platinum. These elements were formed when a star exploded. So what this means is billions and billions of years ago, a star exploded, creating gold. These atoms then floated through space, mixing with the interstellar medium, which, as it cooled, formed into a dark nebula. In a dark nebula, we then have stars form, and around those stars, planets. On those planets, eventually, at least on this planet, life developed, and now we go around digging that gold up and giving it to each other as presents. So what this means is the next time you give somebody jewelry, you can tell them you are giving them a piece of a star, because that's where all of these things came from. Now we can actually test our ideas on if this is where the elements come from by looking at the chemical abundance. The chemical abundance is how much of what elements there are out there in the universe. So on this graph, up and down, we're looking at the amount, how much of stuff there is, and then along the bottom, we're looking at the atomic number. In other words, the number of protons in the nucleus. So we're just stepping from one element to another. So right up here at the very top, we've got hydrogen, and there's tons and tons and tons of hydrogen in the universe. Then we drop down to helium. There's still lots and lots of helium, not as much as hydrogen, but a lot. Then notice we have a huge dip at lithium, beryllium, and boron. There's not very much lithium, beryllium, and boron. Now remember back to as we're talking about all of these different stages of fusion and what elements are being produced. Did we ever really talk about lithium, beryllium, or boron? No, we didn't. Okay, these are not common byproducts of fusion. It is possible to get there, and it happens occasionally, but more often, these things aren't the byproduct. And because they're not something we usually get from fusion, we don't find very much of them in the universe. But then we get a big jump back up at carbon, nitrogen, and oxygen. When talking about different fusion processes, did we talk about carbon, nitrogen, and oxygen? Yes, absolutely. And we see that carbon, nitrogen, and oxygen are relatively common. Every element that it is easy to get through fusion is relatively common, and the elements that are hard to produce through fusion are relatively rare. This is exactly what we would expect if all of these elements are being produced through nuclear fusion in stars.